Before the age of modern power electronics, one device made our electrified world possible: the transformer. From stepping down grid voltages to stepping up power to transmit electricity across continents, transformers are the backbone of our electrical world. On Engineering This, we're diving into everything you need to know about transformers. What is a transformer and how does it work? A transformer is an electrical device that uses electromagnetic induction to change the voltage of an alternating current, AC, without changing its frequency. It's important to note that transformers do not work for direct current DC applications. Unlike motors, it has no moving parts. Instead, it relies on two separated coils of copper wire wrapped around a magnetic core. When alternating current flows through one coil, called the primary coil, it creates a changing magnetic field. That magnetic field links to the secondary coil, inducing a voltage. Let's picture it like this for a second. Imagine a coil connected to an alternating current, AC, voltage supply. This is our primary coil. As the alternating current flows, it produces an alternating magnetic flux. If we take the US supply as an example, that's 60 Hz, meaning the current, and thus the flux, is changing direction 60 times a second. This rapidly changing flux spreads through the transformer's magnetic core. Now enter the secondary coil, which sits within this varying flux. According to Faraday's law of electromagnetic induction, the induced voltage in the secondary coil is proportional to the rate of change of magnetic flux linking the coil and can be denoted from the following equation. In simple terms, the faster and more strongly the flux changes in the primary, the more voltage is induced in the secondary. This induced EMF pushes electrons through the secondary coil circuit, creating a current flow. The magic lies in the turns ratio. The relationship between the voltage in the primary, V1, and the secondary, V2, depends on the number of turns in each coil, N1 and N2, and it can be calculated from the following equation. More turns on the secondary than the primary equals voltage step up. Fewer turns on the secondary equals voltage step down. Most transformers are denoted by the following symbol in electrical diagrams and are usually rated in kilovolt ampere, denoted by kVA. If you're enjoying this deep dive into the world of electronic components, don't forget to subscribe to Engineering This and give us a thumbs up. We've got plenty more tech explorations to come. Check out our online store for unique engineering products and help us keep making awesome content. It really helps us out a lot. Link down below. Another way to support Engineering This is by becoming a member. This will give you early access to all our videos, access to our member-only videos which show how we animate and put videos together, as well as enabling our member-only chat rooms where we can discuss all things Engineering This. Why AC and not DC? Transformers only work with alternating current because they rely on a constantly changing magnetic flux to induce voltage in the secondary coil. With direct current, the flux would remain steady and no voltage would be induced once the circuit settled. This is why Nikola Tesla's AC system beat Thomas Edison's DC in the famous War of the Currents. AC could be stepped up to extremely high voltages for long-distance transmission, reducing current and minimizing losses, and then step back down again to safe levels for homes and businesses. At the time, DC couldn't do this economically, since no practical method existed to change voltage levels. Only with modern high-voltage direct current HVDC technology developed decades later did DC find its niche in the very long-distance interconnections and undersea cables. But for everyday grids, AC remains in use thanks to its natural compatibility with transformers. The anatomy of a transformer. At the very heart of a transformer lies the core, a stack of thin laminated steel sheets. These laminations are carefully insulated from one another, producing eddy currents and guiding the magnetic flux with minimal energy loss. Wrapped around one side of the core is the primary coil. This coil is connected directly to the input AC supply, As alternating current flows through it, the coil generates a changing magnetic flux that the core channels and concentrates. On the opposite side, wound around the same core, is the secondary coil. This is where the energy arrives, induced by the flux shared through the core. The voltage here depends entirely on the ratio of turns compared to the primary, making it either step up or step down in function. Surrounding these coils is the insulation system, a barrier that prevents electrical breakdown between coils and the core. Depending on the transformer's size and application, this insulation may be reinforced with paper, resin, or high dielectric polymers. To keep everything stable, large transformers are immersed in cooling mediums, typically mineral oil or modern synthetic alternatives. The oil doesn't just insulate, it circulates heat away from the coils, sometimes aided by radiators or forced pumps. Smaller distribution transformers rely on natural air cooling, while compact electronics often use encapsulating resins or forced ventilation. Mounted on the exterior are bushings, solid insulating sleeves that allow high voltage connections to safely pass through the grounded transformer tank without electrical discharge. For transformers that need flexibility, especially in power grids, tap changers are built into the winding design. These devices let operators adjust the effective number of turns on the coil, fine-tuning output voltage to balance supply and demand in real time. Encasing the entire assembly is a protective tank or shell, shielding the delicate internals from dust, moisture, and mechanical stress, while allowing the transformer to operate reliably for decades. Types of transformer. Not all transformers are built the same. Each type is carefully designed for a specific role in the journey of electricity. Let's break them down. At the top of the chain are power transformers. These are used in transmission networks working at extremely high voltages, often hundreds of kilovolts. Their job is to connect generating stations to the transmission grid, stepping voltage up or down between major tiers of the power system. They're optimized for maximum energy, since even tiny losses at this scale translate into huge amounts of wasted energy. Next, we come to distribution transformers. Smaller than power transformers, these are the ones you see perched on utility poles or tucked inside street cabinets. Their task is to take medium voltage electricity from the grid, say 11 kilovolts or 33 kilovolts, and step it down to the familiar 230 volts in Europe or 120 volts in the US, making electricity usable for homes, schools, and factories. Then we have isolation transformers. Unlike step-up or step-down types, these don't change voltage ratios as much as they provide electrical separation. By physically isolating the primary and secondary coils, they prevent noise, interference, and dangerous surges from passing through. Hospitals, laboratories, and audio equipment often rely on them for clean, safe power. Finally, there are autotransformers. Instead of two separate coils, they use a single coil tapped at different points to act as both primary and secondary. This design saves copper and space, making them more compact and efficient for certain applications, like adjusting voltage in long transmission lines or providing variable voltage in labs. However, because there's no full isolation between output and input, they're less suited where safety separation is essential. Transformer losses. No device is perfect. Even the most efficient transformers lose a little energy in the process of transferring power. These losses appear in several forms. At the coil level, there are copper losses. As current flows through the primary and secondary coils, the resistance of the copper wire turns some of that energy into heat. This is often written as I2R loss, proportional to the square of the current. Inside the core, we see iron losses. These come in two main forms. Hysteresis loss, energy consumed every time the magnetic domains inside the steel core realign with the alternating flux. Eddy current loss, tiny circulating currents induced in the core material itself, which waste energy as heat. Not all magnetic flux makes it from primary to secondary. Some escapes the core entirely, creating leakage flux, which slightly reduces the efficiency of energy transfer. Engineers work hard to minimize these effects. They use laminated cores to cut down eddy currents, high-grade silicon steel to reduce hysteresis, and low-resistance copper windings to limit I2R heating. For large units, oil cooling and radiators help carry away excess heat, keeping efficiency high. Modern transformers are remarkably effective, often above 98 to 99% efficiency. But understanding these subtle losses is key to designing machines that can run reliably for decades. Next time you plug in your phone or see power lines overhead, remember the humble transformer is silently doing the heavy lifting.